So with this increasing, decreasing, right, link to the derivative, right, where our function is increasing when our derivative is positive, and our function is decreasing where our derivative is negative, it sort of starts to beg the question of what does it mean when the derivative equals zero? And this is a thing that I've teased a couple times in our course. Um, and now we can actually take a look at it. Okay, so I'm going to throw a graph up. There's a much better graph of this in the book, or just about anywhere online. But if you were to look at the budget surplus in the U.S. From 1996 to 2008, right? It's going to look roughly something like this, and it kind of goes up and then down. Okay, where I'm, excluding any sort of scale here because that's, sort of not what we're looking at, right? We're just sort of grabbing a graph, and so what I want to draw your attention to, right, is here our function is increasing and here our function is decreasing, and we can use our derivatives, right, to look for increasing and to look for decreasing, and what we can also have it look for these sort of these high points and these low points, right? They're called relative extrema. Okay, relative meaning in a local area, and we'll firm all of this up in a second. And then extrema meaning there are sets of extreme points, right? One extremum, multiple extrema, right? And so let's sort of take a look first at the relative maximum. Okay, so a function f has a relative maximum or local maximum. Those words are interchangeable. At x equals c, if there is some open interval we'll call it AB. This interval contains C such that, and this is the important thing, f of x is less than or equal to f of c for all x in AB. So what does this mean, right? What's the idea behind this definition, right? Does it do what we expect, right? Because that's sort of one of the things with parts of calculus is like you can look at this graph and you can tell me, hey, this should be one of our local maxima. This should be a local minimum, right? This should be a local maximum. And does this definition do what we would expect, right? So let's, I don't know, grab a function like that, say, and we should expect this guy and this guy are our local maximums, right? And what our definition is saying, right, is that around each of these, so say we'll call this C1 and this C2, that around each of these I can find some interval around it where it's bigger than everything else, right? That's what this is saying, that everything else in that interval is less than or equal to, say, f of C1, right? And, well, it seems like we can do that, right? If we say pick, I don't know, this interval here for that one, then any element you could possibly pick out of here is going to be less than this, right? Similarly, we can pick these intervals to be tiny, or we can pick them to be a little bit bigger like that, right? But everything in this interval if you compare it to this point, it's going to be less than or equal to. And you might also be curious, right, about what about points that are the biggest on any interval, right? And we'll get to that next week. We'll take a chance to sort of discuss like looking for the biggest value of the function everywhere, not just in some sort of local interval. Or the other word you'll hear there is that this is called a neighborhood of that point, right? This sort of little interval around it is sometimes called a neighborhood. And for our idea of a local minimum, we can actually take this, copy it, and just change a few words, right? So we're looking for a local minimum, right, at x equals c. If there's some open interval, a and b, around it, right, such that, and this is the other big change we make here, and it should, sort of track with what you would expect. F of x is greater than or equal to f of c for all x in that interval, right? And we would expect this would be a local minimum, and somewhere around there would be a local minimum, right? And we can project this down, maybe we'll call this M1 and M2, right? And we can pick, maybe this one we'll pick an interval that's that big. And then for this one, we can pick a little tiny interval, right? Nothing's stopping us from going tinier, right? And in that interval, right, f of m2 is smaller than everything else in that interval, okay? So then, of course, the question becomes, right, how can we actually find a relative extrema, right? How can we look for them? And the first way that we'll sort of look for them is to look at functions that are differentiable at those points, right? Before we sort of expand our ideas to more complicated functions, let's just look at the simple ones, okay? And here's what I want to draw your attention to, right? Let's take a function, and let's say it looks something like that, okay? Here's what I want to sort of do with you, right? Let's take a look at what our derivative is doing. Well, if we're looking for this particular local minimum, right? That's what we're looking for. Notice if we just sort of graph a handful of tangent lines really quickly, if we're sort of over on this side, right? We can pick some representative point. We can pick some representative point for this interval and drop a tangent line to it, right, where I've made my line a little bit thinner so it doesn't obscure what's going on in the graph. But we can see here, right, our derivative is negative. And then again over here, if we drop some representative tangent line, maybe to, looks like that's tangent to this point, right? Notice here that my derivative is positive, okay? But what's going on right here? Well, at this local minimum, if I drop a tangent line, my tangent line is flat, right? F prime of x is equal to 0. And notice that here, where we have this local minimum, our tangent line, so our derivative, has slope 0, okay? And you could absolutely make the exact same argument, right? If you took this graph and you just flipped it vertically, right? If we were looking at something like this, our tangent line here is now positive, right? Maybe at that point. Our tangent line here maybe at that point is negative, and our tangent line right at that local maximum is flat. Okay. So there is some deep connection between our tangent line being 0 and our local maximum or minimum, right? But that's not quite the full story, unfortunately, right? And what we can do with that is we can take a look at say f of x equals x cubed, right? Well, then f prime of x is 3x squared, which means f prime of x equals 0 when x equals 0. So we've done it, right? F of x equals x cubed should have a local extrema at x equals 0. But as we know from our parent graphs, that's not the case. So it means we have to be a little bit more careful, right? Also, consider something like this, right? What if we took a look at the graph of the absolute value of x, right? The absolute value of x absolutely has a local minimum right there. Absolutely. Its derivative there is not defined, right? Similarly, if we were to say take a look at the graph of say y equals x to the 2/3, right? Something that we looked at in the last part of the lecture. Well, this guy's going to look like this, okay? Where sort of these two come to a point. Once again, we see that we should have a local minimum right here. But our derivative doesn't exist there, as we saw in the last part. But this should sort of get our minds churning, right? Just as in the last point, our important points, the points that sort of separated increasing from decreasing, those were the places where our derivative was 0 or didn't exist, right? And here we see where the derivative doesn't exist, we might sometimes get local minimums or maximums. And then, when the derivative equals 0, right, sometimes we get these nice local extrema, and sometimes we get this slide, right? And we'll take a closer look at the slide actually at the beginning of next week. We'll sort of explore, what this is doing, right? And we'll actually need to use the second derivative to understand it. But we can sort of put all of this together and define a new term, right? So a critical number of f, you'll often also hear these guys called critical points, but they are any number x in the domain of f such that if prime of x equals 0 or f prime of x does not exist, right? And here's what these will allow us to do, okay? Is it will give us candidates for finding local extrema, right? If we were to just, throw some weird function on here, maybe it goes up and then down, and then it, does a little slide, and then it hits a corner, and then, it does something like this, right? At these points, right, we're going to have horizontal tangent lines, right? Here we're looking like a local maximum. Here we're looking like a local minimum. Here, at this sharp corner, our derivative doesn't exist, but we still have a local maximum right there. Here, we're going to have a vertical tangent line. I guess, you can sort of see I went a little bit over, but, we'll say that this guy goes straight through. So sort of like this slide, but on its side, right? And so these unique places, these critical numbers of f, turn out to be where we can turn out to be our sort of tools and our guides for finding local extrema. And this leads to a little something called the first derivative test. Okay, and I've cooking showed it up on the next page for you, but I want to sort of give you the idea, right? Notice that the big difference between these extrema and these things that aren't extrema is here my derivative goes from positive to negative, but here it goes from positive to positive. Here it goes from negative to negative, but here it goes from negative to positive, right? This is the key insight of the first derivative test, right? If you have some critical number of a function that's continuous in some local, neighborhood around it, okay? If it's differentiable on that interval, except for possibly there, right? This is a bunch of important things to classify the ideas, but they just sort of describe, hey, look, if you can zoom in and it's differentiable around it, right? Then one of three things occurs, right? Foresee some critical point. If the derivative changes from positive, right? The derivative goes from positive to negative, well then our critical point that's in the middle is a relative maximum. Similarly, if our derivative goes from negative to negative, from negative to positive, well then our function has a relative minimum, right? And if it does not change sign, well then f of c is neither, right? If it doesn't change sign, well then it's something like this, right? Positive derivative here, positive derivative here. Negative derivative here, positive derivative there, right? That's sort of the genius of the first derivative test, is we don't have to just be like, okay, well, here are our critical points. Some of them might be extrema, some might not be. We can simply look for, well, what does f prime do around it? Okay, let's take a look back at some examples. Okay. Right, we'll sort of work through some of the examples that we did in the last part, right? So let's say find the relative extrema of, and then we'll break this into parts, right? First, we'll start with f of x is x cubed minus 3x squared minus 24x plus 32, right? And if we remember, our derivative is going to factor into 3 times x plus 2 times x minus 4. And you know what? We already did all the work here, right? Because if we remember, we have negative 2 and we have 4. And we're negative on this interval, 0 there and there, right? This negative 2 and this 4 are our critical points. We're negative here and we're positive there, right? And so what that means is that at negative 2, we're going from a positive to a negative. So that means negative 2 is a local max, right? In particular, right, if we wanted to calculate, right, f of negative 2, if you go through negative 2 cubed minus blah, 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 you're going to get that that's equal to 60. So this f of negative 2 equaling 60, that's a local maximum, right? If you take a little neighborhood around the point, everything around it's going to be less than it. Similarly, 4, right? 4 is going from negative to positive, which means this is a local minimum, right? And if you were to say, look at f of 4, this would come out to negative 48. And later in probably early next week, we'll sort of look at graphing these guys, right? If you remember from pre-cal, most of the time when you are graphing these big polynomials, you were just sort of sketching a graph from the zeros. And like I said, we'll take a better look at it next week. But your graph is going to look something like this, with this as negative 2, and this is 4, right? And so, drawing the graph to say, this graph does actually do what we would expect, right? If you plugged this, into your favorite graphing calculator, then it would spit something out that looked like this, with those, local extrema where we expected, okay? And then, I don't remember what I called it. I think it might have been h of x is x plus 1 over x, right? Our derivative was x squared minus 1 over x squared. And so what are our critical points of this? Well, our critical points are the exact places before that we had called our important points, right? It's negative 1, 1, and 0. Negative 1 and 1 being zeros of the function, and 0 being a place where it's discontinuous. And as well, we had, this sort of line, right? This line with the points of your critical points. That's almost always how you'll do this first derivative test, right? We remember we had 0 does not exist in 0, right? Showing that these are indeed our critical points. We were positive here, we were negative here, we were negative here, and we were positive there. And so that's going to tell us once again, here we're going from positive to negative. So this is a local maximum. And in particular, f of negative 1 is negative 2, right? And here we have a local minimum where f of 1 is going to equal positive 2, okay? But just from looking at how the sign changes, here we can determine those. Here in the middle, this is a critical point, but see, it's, quote, changing from negative back to negative. And so that's going to tell us that while it is a critical point, it doesn't represent a local extrema. And in particular, graphing functions like this was covered in pre-cal, but I will sort of give you the idea of what it's going to look like. It's going to have an asymptote like this, and again, we'll cover curve sketching in more detail next week. It's going to look like this, right? With our local maximum here and our local minimum right there, okay? We can turn our attention now actually to sort of, these to something with a little bit more, I guess, practicality, and that's profit functions, right? Say you have some profit function negative 0.02 x squared plus 300x minus 20,000, right? You know that this is a parabola, right? You know for sure that it's a parabola. And so you know that since it's a parabola that's facing down, it's got to have a local maximum somewhere, right? The vertex of this parabola. And in pre-cal, there's all sorts of little things that you can memorize to shortcut to this, or we can just take a derivative, right? Because p prime of x, well, it's going to be minus 0.04x plus 300. And since we know the parabola is only going to have one local extrema, it's going to happen where p prime of x equals 0, right? This is just a line facing down. And further notice, if I were to factor out a negative 0.4, it's going to be x minus 7,500. And this is sort of working backwards from the other ways that we did it, right? But we can see clearly now that our profit function's derivative, right, is going to have a 0 at 7,500, right? Because 7,500 minus 7,500 is 0. Further, we can tell, maybe by just, plugging in 0 to this, we can tell that p prime of x is greater than 0. This will say on the interval 0 to 7,500, right? So here, since our derivative is greater than 0, the profit function is increasing on that interval. Likewise, p prime of x is going to be less than 0 on 7,500 to, arbitrarily far. After 7,500 units, our profit function is decreasing, okay? And like I said, when you're using a computer to model these businesses, these functions are not particularly hard to get, and we can analyze them and find exactly where our profit function should be with relative ease, okay? That's going to wrap it up for this lecture. Like I said, next week we're going to look at what the second derivative can do for us, and then turn our attention to sort of, sketching graphs of these curves using this information.